Live.
Siamo live.
Great. So thank you everybody for being here. Welcome to the first day of this school that is gonna take company for the next 3 weeks. So I see that some of you are connected from the very east, so it's late afternoon. Some of you from the west, so it's very early morning. So thank you for making it. So today we are going to have 3 slots. So if you have not watched it, please go to the program page, and there is going to be a link for the sort of full introductory remarks by the organizers. So today we're going to have 3 slots. In the first one, Leonardo is going to give a tutorial on nonlinear dynamics, and it will be followed by a lecture by Joshua Weitz and a lecture by Carla Stadler. So a little bit of an etiquette before we start. So this is a large meeting, so please unmute yourself, unmute the microphone. During the meeting, if you have a question, please raise your hand, and the moderator will stop the speaker, or when there are enough questions, will be stop the speaker to have you asking questions. Okay. So in particular, the first slot is a tutorial, so it's meant to be very interactive. So please, if something is unclear or you want clarification, please don't hesitate to ask questions. As you have seen, in between lectures, we have a 50-minute buffer. So lectures and tutorials are going to be 1 hour long, and there is a 15-minute break. So in those break, I mean, you can, of course, stretch your legs, get a cup of coffee, but we also will divide all the participants into breaking rooms, and you will have the opportunity to interact very informally with other people that are attending. You are free to stay in the room you are randomly assigned to, or change room, interact or not interact. This is just an informal opportunity to know other people. So, okay, in perfect timing, I think I can introduce the first speaker, who is Leonardo Pacciani-Mori. He's a PhD student from the University of Padova. And today and tomorrow, he will give a tutorial on nonlinear dynamics. So please, thank you, Leonardo, for being with us, and I'll give you the floor.
Thank you for inviting me. So let me share the screen so you can see my slides, right?
Yes.
Perfect. So hi everyone. Thank you, Jacopo, for the introduction. So today and tomorrow we will be talking about nonlinear dynamics. So let me first show you how I have organized all the material for today's and tomorrow's tutorial, and then we can get started right away. So I will start with a very simple and brief introduction, just to remind ourselves what are nonlinear systems, why are they interesting, and I will also give you a few examples with a particular focus, of course, in ecology. Then I will show you how, for example, by using stream plots, we can actually understand the general behavior of the solutions of a nonlinear system without actually solving the equations analytically. Then we will be talking about stability in nonlinear systems. In particular, I will show you the 2 main tools that can be used to study the stability of equilibria in nonlinear differential equations. Of course, throughout all these topics, I will show you plenty of examples. We will also do a couple of very simple exercises. So we will get a practical sense of, we will get our hands, let's say, on the topic, and so we can better understand what we're doing. Now, as Jacopo already told you, these tutorials are, I mean, they shouldn't be just simple lectures, but they are meant to be a moment of discussion. So please, at any time, if what I'm saying is not clear or if you have questions, please ask me. So if everything is clear for now, we can get started. So what we would like to do in general is, let's say, solve or understand something about nonlinear differential equations. Now, by nonlinear differential equations, we basically mean an equation or a system of equations that look like this. So where this function f here is any nonlinear function. So these, for example, will all be simple cases. They can be in one dimension or in two dimensions here, where this function is nonlinear. So these are all simple examples of nonlinear system. And they are interesting, and we want to be able to understand something about them, basically because any interesting phenomenon in nature is described by a nonlinear differential equation. Let's see some example. One of the, I think, most simple but also overlooked physical system that is actually described by a nonlinear differential equation is the pendulum. Now, you may be used from introductory physics courses to see this equation with sine of theta approximated by just theta, but that is only an approximation of the true, let's say, pendulum equation, which is actually a nonlinear one. Then another important case where of nonlinear system are fluids, because fluid dynamics is regulated by Navier-Stokes equations, which generally are nonlinear equations. For example, this is the equation for an incompressible fluid, where u here is the velocity field of the fluid, and this term, for example, we can see that is not linear. So again, fluid are an important example of nonlinear system. Now I want to introduce two examples that we will consider over and over again in these tutorials and that are actually relevant for ecology. The first one is the logistic growth equation. You may already have seen it somewhere at some point in your life, but basically this equation simply describes the growth of a population X in a system with, let's say, a limited amount of resources. Now, of course, I'm going to show you this in more detail in a few slides, but basically you see that if we didn't have this term here, this equation would basically be a simple linear differential equation, and so we would have that the population X here is growing exponentially without limit. But this term, as I will show you later, basically makes it impossible, for the population to be larger than K. So this system has a maximum population, let's say, that can be sustained. The other system that is relevant for ecology is Lotka-Volterra equations. Again, this is a very famous system which basically describes the dynamics of the population of a prey, which is X here, and a predator, which is Y here. And these parameters basically measure the interactions between these two populations. You see that in both cases here and here, the functions that define our differential equations are nonlinear. So these are indeed nonlinear systems. Okay, so what we would like to do generally with, let's say, an ideal world with nonlinear differential equations would be to solve them analytically. But unfortunately, this is almost never possible because we don't have like a theorem or a general recipe, let's say, that can give us a direction into how to solve any given nonlinear system. So it is reasonable to ask ourselves if and how we can understand something about nonlinear systems without actually solving the equations. Now, what people generally want to do with nonlinear systems is studying their equilibria. Now, I'm going to introduce definitions that probably are very familiar to you, but I just want to first refresh their meaning, and then I also want to build a small vocabulary on nonlinear system that can be useful throughout this course. Now, in general, if we have a general nonlinear system like this, a given point x star is said to be an equilibrium of the system if the function that defines our equations here is equal to 0. You see that this means basically that the equilibria of a system are the points where the variable doesn't change, because if x is equal to x star, then f is 0, x dot is 0, and so the variable will not change once it is equal to this equilibrium here. Now, what people generally want to do with equilibria is understand if they are stable or unstable. So we need some notion of stability and instability to study them. So let me introduce some very informal definitions of stability and instability. I will make these definitions a little bit more formal in a few slides, but I just want you to get an intuitive idea of what I mean. So in general, an equilibrium is said to be stable if any solution of the system that starts with an initial condition that is close enough to the equilibrium will always remain close to x star. Now, of course, this notion of closeness, close enough, is anything but rigorous, but still, I just want you to get the intuitive idea for now. On the other hand, an equilibrium is said to be unstable if it is not stable. So if we can find solutions of the equations that start close to the equilibrium and eventually go away from it. Now, in light of these concepts, we can basically reformulate our initial question as follows. So can we understand something about the stability of the equilibria of a nonlinear system without actually solving its equation? The answer, of course, is yes. There are several ways, several tools that we can use. And one of the simplest one, but also quite effective that we can use in this direction is drawing stream plots, which basically means drawing the trajectories of the system in the state space. Now, I think the easiest way to understand how stream plots work is to see how they are done practically. So let's start with a simple example. So assume we are given this differential equation, which is of course nonlinear, because this function here is a simple cubic function. So let's draw it. This function basically looks like this. And so we can see very easily, we can also factorize the expression in this way. So we can see very easily that the system has three equilibria in this case, which are the 3 points where this function is equal to 0. In particular, in this case, are -1, 0, and 2. Now, the basic principle behind drawing stream plots is the following. Now, wherever this function f here is positive, x dot will be positive. So the solutions that start from point where f is positive will be characterized by the fact that x is increasing. So for example, if we consider this interval here between -1 and 0, in this interval, the function f is positive. So any solution that starts from these points here will be characterized by the fact that x is increasing. And the same will happen, for example, in this interval here. On the other hand, wherever f is negative, x dot will be negative, and so the solutions will be characterized by the fact that x is decreasing. So if we start from any point in this interval here, we will have that the solutions actually go towards the left, and the same here. So in the end, what we can draw are these trajectories. So this is the stream plot of our system. And so you can see that by doing this very, very simple drawing, we can already guess which equilibria are stable and which are unstable. In particular, we can guess that this equilibrium here is unstable, because you see that if we take any initial condition that is slightly larger than 2, we will have that this solution basically increases without limit, and something similar happens here if we take an initial condition that is slightly lower than -1. On the contrary, we see that solutions here are actually going towards the equilibrium in 0. And so we can guess that this equilibrium is stable. Let's see another. Is everything clear here? Okay.
So I think it's a good time if you have a question, something.
Yeah, exactly.
To ask a question. So please remember that this is a tutorial. So this is really meant to have everyone being on the same page on the topic. So if something is unclear, don't hesitate to ask questions. Okay.
Okay. So let's see basically the same thing applied into a different case. So let's consider this equation, x dot equal cosine of x. So in this case, we know that our function here looks like this. So we will have basically an equilibrium in every positive and negative odd multiple of pi halves, because these are the zeros of the cosine function. Then if we apply the same principle as before, we will have, for example, that in this interval here, in this interval here, and in this interval here, the function is positive. So the solutions will going towards the right. On the other hand, in this interval here and in this interval here, the function is negative, and so the solutions will be going towards the left. So in the end, the stream plot that we can draw of this system looks like this. So you see that in this case, we basically have an alternation of stable and unstable equilibria in our state space, which of course is the x-axis here, because this system is a unidimensional system. We only have x as a variable. So let me now show you basically how we can use these stream plots in cases that are ecologically relevant. So the first thing I want to show you is the stream plot of the logistic equation. Now, actually, this is one of the few lucky cases where we can actually solve an equation analytically. So I hope that with this example, it will be clear that, I mean, comparing what we see with the stream plots with what we see with the analytical solution, that stream plots can actually help us understand the general behavior of the solution of a nonlinear system. So first thing, let's try to, let me show you how these equations can be solved analytically. So let me write here in the whiteboard the equation. Okay. So to solve this equation, I'm going to use some physicists' tricks. So if you are a mathematician, I apologize because you will probably be horrified by what I'm going to do. But basically, what we can do in this case is we can separate the variables. So we bring everything that depends on x on one side and everything that depends on t on the other one. I'm sorry, this whiteboard is a little bit slow, but I hope you can see everything. So once we have done this, now this fraction here, we can actually decompose it into two terms. So we can write this as dx over x plus dx over k over 1 minus x over k. So you see that if we simply add these two fractions, we get exactly this. So we have this equation. But these are very simple terms to integrate because, for example, this one will be the logarithm of x plus a constant. This one will be minus the logarithm of 1 minus x over k plus a constant. And this here will be simply RT plus a constant. So in the end, we can rewrite everything as logarithm of x over 1 minus x over k equal to RT plus c, which basically means that x over 1 minus x over k is the exponential of RT plus c. Now, of course, we have to determine the value of this constant, so we can evaluate this expression for t equal to 0. And by simply rearranging basically the expression that we get in this way, the final analytical solution of the logistic equation looks like this. So this is the analytical solution of this equation, where x0 is, of course, the initial condition on x. Now, you see that here we have an exponential with a negative exponent, because remember that both r and k are positive parameters. So as time passes, so as t becomes larger and larger, well, we can neglect basically this term here. Then x0 and x0 cancel out, and so we can see that the solutions of this equation tend towards the value k. The only case in which this doesn't happen is when the initial condition is 0, because you see that in this case, if x0 is equal to 0, the numerator... Is there a question?
Hello.
Yes?
Yes, yes. So could you explain what is R and X and K?
Yes, of course. Basically, the biological meaning of R is the growth rate of the species. You see that if we didn't have, let me write it down. If we didn't have the quadratic term, so if we had only this equation here, the solution of this equation would simply be, constant times RT, would simply be an exponential. So in this case, we would have like a population growing exponentially. The biological meaning, on the other hand, of this other parameter, and it's going to be clear in a few seconds, but basically this is the maximum population that the system can sustain. Because let me draw basically how the solutions are. So for example, if we start from x0 equal to 0, as I've just told you, basically the solution is constantly equal to 0. So this is a trivial case because it basically describes a system with no population. Something similar happens also when x0 is equal to k, because you see that here we would have k minus k, so this is always equal to 0. And again, this and this cancel out. But then, if we take any initial condition between these two values, this function basically behaves like this. So we have a population that grows, and the initial growth here is actually an exponential growth, because you see that when x is very small, we could neglect it. So at the very beginning, the growth is well approximated by an exponential, but eventually this population saturates towards k. On the other hand, if the initial condition is larger than k, what happens is that the population quickly decays towards k. So basically, the meaning of this parameter is the maximum population that the system can sustain. Because basically, the idea behind the logistic growth equation is that the population here, this could be microorganism, could be animals, could be anything, but it is in an environment with limited resources. So at a certain point, the system will reach a population that is not sustainable anymore. And so x cannot grow larger than k. And even, you see, even if x is driven to a value larger than k, then it quickly decays back to k. Does that answer your question? I mean, was I clear enough?
Yeah, that's clear.
Okay.
Please request to all, please don't put the message regarding the wishes, okay? Irritate.
Sorry?
Okay, it's correct, it's okay.
Okay. So the fact that k here is basically the maximal population of the system is also why this parameter is called the carrying capacity of the system. So now we know how these solutions work. In particular, if we look at what is happening in the state space, so along this axis, you see that these solutions here basically are going towards k, and in the same way, these solutions here are going down towards k. So let's see if we could understand this general behavior already from the stream plot. So again, this is our equation. The function, the nonlinear function that describes the system now is simply a parabola, and so we can draw it. Now, of course, here I am not considering the negative part of the state space, simply because this variable here represents a population, so it makes sense only when it is non-negative. So this is the aspect of this function. So we see immediately that we have two equilibria, indeed, 0 and k. So now let's apply what I've shown you before for stream plots. In this interval here, the function f is positive, and so the solutions, the trajectories of the solutions will go from 0 to k. On the other hand, in this other part of the state space, the function here is negative, and so the solutions will move again towards k. So in the end, the stream plot of the system is like this, from which, I mean, we can also guess that this equilibrium here is unstable because the solutions are moving away from it, while this equilibrium here is stable. So you see that if we look at what is happening in the state space, we are actually recovering the same behavior. So of course, by using the stream plots, we can't say, for example, how quickly these trajectories are moving or the exact way in which this is happening. We couldn't guess, for example, that there is an exponential, like I've shown you before, that regulates the speed of this motion. But again, without even trying to find the analytical solutions, we can see how the solutions are moving in general. Now, if everything is clear here, so if there are no further questions?
There is a question.
Sorry, can I
Okay.
ask?
Yes, of course.
What does it mean of unstable and also stable?
By unstable and unstable, in this case, I'm meaning the very informal definition that I have given a few slides ago. So unstable in this case means that the solution are moving away from the equilibrium, because you see that in this case, if you pick any initial condition that is slightly larger than 0, the solutions will eventually go away from this equilibrium. While on the other hand, stable equilibrium means that the solutions are remaining close to the equilibrium. So in this particular case, for k, for example, we have that the solutions are actually going towards the equilibrium, but this is not necessary for the equilibrium to be stable. So this is a particular case of stable equilibrium. In general, for an equilibrium to be stable, we just need that the solutions remain close to it. Does that answer your question?
Yeah, thank you.
Okay, no problem. So I hope it is clear with this example that I mean, what we are seeing with the stream plot makes actually sense if we compare it to the analytical solution.
Can I ask?
Yes, of course.
So ecologically, it means that the K is
Yes.
the point where it achieves equilibrium, right? So there's
Yeah.
no resource limitation, like we can say, for the growth.
No, the resource limitation is, I mean, is in the fact that this population is not growing exponentially. If we had a system where an unlimited amount, where we had an unlimited amount of resources, basically here we would have only an exponential growth with a fixed growth rate, basically.
Okay, okay.
What happens in this case is that K is the, I mean, is the maximum population that can be sustained by the system, meaning that if for any reason the population grows larger than K, there are no enough resources to sustain that population. And so you see that eventually the population will go back to K.
Okay. Perfect.
So in this case, is there is, in this sense, there is resource limitation.
Okay.
Okay. So what we can do now is basically apply the same thing. So we can try to draw the stream plots in the case of the Lotka-Volterra system. So our equations in this case are this, and this is our state space. Again, here I am considering only positive values for X and Y because they represent populations. So it doesn't really make sense to look at the other quadrants of the state space here. So if we look at these equations here, we can find very easily two equilibria, which are the origin, the origin and this non-trivial equilibrium. Now, the origin is very easy to see why this is an equilibrium, because if X and Y are both equal to 0, then both X dot and Y dot here are 0. The other non-trivial equilibrium is very easy. Let me show you. For example, we have that X dot is equal to alpha X minus beta XY. So if we want this to be equal to 0, we can rewrite this as X times alpha minus beta Y equal to 0. So if X is not 0, we simply have that Y is alpha over beta. If we do this exact thing with the other equation, we get that the equilibrium in the end is this point here. Now, let's try to draw the stream plot. The first thing that we can do is see how the system behaves on this axis here. So, for example, if we take an initial condition where x0 is equal to 0, so we start from the y-axis here, you see that our...
There is a question, Leonardo.
Yeah, sorry. Am I having problem with the audio? Or...
Can you hear me? Can you hear me?
So yeah, I think I can hear you. Yes.
Can you hear me? Can you hear me?
Okay.
Okay. Please. What if the K is not constant? So what do we do? What if the K doesn't come constant?
I'm sorry, I'm not hearing you well. There is a little bit of background noise. I'm not...
I think that the question was is not constant.
Sorry?
The question was what if the carrying capacity is not constant?
What if the carrying capacity here? Okay, you mean here? Well, in this case, we would have basically a different system. K could be a function of X, if you want, or a function of any other variable. But I mean, it would simply be a different system. We would require, it would have a different stream plot. So we can use the same tools, but it would be simply a different system. Okay. So where were we? Okay, so if we take an initial condition, for example, that is on the y-axis here for the Lotka-Volterra system, you see that our system reduced to this. So the solutions basically will be decaying exponentially towards the origin. Remember that all these parameters here are positive, so minus gamma y is negative. On the other hand, if we take any solution that starts on the x-axis, so if y0 is equal to 0, we can write our system like this. And so the solutions will be growing exponentially on the x-axis. So the first thing that we can draw about the stream plots are these trajectories here. And this, again, notice that it would be enough for us to guess that the origin here is an unstable equilibrium, because you see that along this direction, we have solutions that actually go away from the equilibrium. So by definition, this equilibrium here would be unstable. So let's try to see what happens, in the rest of the state space. What we can do is see exactly when the components of this function here are positive and when they are not. So for example, if we look at when x dot is positive, we have, again, as I've shown you before, that this must be positive. Now, we are not on the y-axis, so x is different than 0. And in the end, we get that y must be lower than alpha or beta. So we can divide the state space into two regions, one where x dot is negative and one where x dot is positive. Similarly, if we look at where y dot is positive, we get that this is true when x is larger than gamma over delta. So in the end, we can basically divide our state space in 4 regions. And for each of these one, we know that x dot and y dot is either positive or negative. This basically means that we are able to see the general direction, let's say, towards which the solutions are pointing. For example, here, if x dot and y dot are both positive, it means that the solution is growing both in x and in y. So in general, the solution is pointing in this direction. And this is true also for these other areas. So you see that we haven't even tried to solve the equations, but we can guess already that the solutions of the Lotka-Volterra system oscillate around this equilibrium. Of course, we don't know exactly how this happens, but we know that this is happening. Is that clear? Are there questions? Okay. So I hope it is. Sorry, I was muted. So I hope it is clear now that stream plots are actually useful to understand the general behavior of the solutions of a nonlinear system. But of course, the powerfulness of this approach is limited because we can't always understand something about the stability of the equilibria. For example, if we consider this case here, we know that the solutions are oscillating, but we can't say anything on the stability of this equilibrium, because we could have that the solutions here are spiraling towards the equilibrium. We could have that the solutions are spiraling away from the equilibrium, or we could have any kind of behavior. So in this case, we can't say anything about the stability of the equilibrium. So how we can study in general the stability of equilibria in nonlinear system? There are two main tools that can be used in this direction, which are Lyapunov functions and spectral analysis, which is also known as simply linearization. Now, is anything clear up to now? Okay, so before I go on and I talk about how to use the Lyapunov function, I want to introduce the formal version of the definitions that I have given you before about stable and unstable equilibrium. So we consider a generic nonlinear differential equation and assume that we know x star is an equilibrium. Now, using the language of mathematician, now I'm not a mathematician, so I won't be very formal, but I just want you to let you know how the formal definition of stability is. So this equilibrium in the language of mathematician is said to be stable if for every neighborhood A of x star, there is a neighborhood B in A, such that the solution starting from points in B will always remain in A. Now, this is just the formal way to say what I told you before, which means that an equilibrium is stable if every solution starting close to it always remain close to it, where the notion of closeness in the language of mathematicians is given by the use of neighborhoods. So let me show you graphically because I think it's easier to understand this way. Now, assume we have an equilibrium here. Now, this equilibrium will be stable if for every choice that we can make of a neighborhood A, so a set on the state space that contains this point, we can always find a smaller set, B, and if we pick any point inside here and we use it as the initial condition of our nonlinear system, the solution starting from here it can move around all it wants, but it will never go out of A. So it will always remain close to the equilibrium in this sense. Now, if this is true, I want to introduce a couple of other definitions of stability, because I mean, this way we can build this vocabulary that will be useful throughout the school. Now, if this definition of stability is true, not only, let's say, in the future, so looking at how the solution behaves for positive time, but if this is true also for negative time, we say that this equilibrium here is not only stable, but stable at all times. On the other hand, if this solution here, instead of going around this set A here, at a certain point, it moves toward the equilibrium. So if the limit of the solutions is the equilibrium, we say that the equilibrium is asymptotically stable. So the difference between a simply stable equilibrium and an asymptotically stable equilibrium is that in the asymptotically stable equilibrium, we know that the solutions are moving towards the equilibrium. While if an equilibrium is simply stable, this doesn't necessarily happen. Is this clear? Are there questions? Okay. So the other side of the coin is instability. So again, using the language of mathematician, an equilibrium is said to be unstable if it is not stable. So if we can find at least one neighborhood of X star such that for any choice of a smaller neighborhood, there is always at least one initial condition such that its solution goes out of A, which again is just the... Yes? Yes?
So, Shamolina, sorry for misspelling the name. You have raised the hand.
Yeah, I have a question. I could not understand the difference between asymptotically stable and normal stable equilibrium.
Yeah, of course. The difference basically is in the fact that if an equilibrium is asymptotically stable, it means that we know that the solution is actually going towards the equilibrium.
Yes.
While if an equilibrium is just stable, so not as stable but not asymptotically stable, then the solution is not going towards the equilibrium. It can be oscillating, it can be going around the equilibrium, but it's not actually going towards the equilibrium.
Then why you are calling it stable if you don't know its fate? I mean, ultimately when it will go towards that equilibrium, then we can call it stable, right? Then in what sense you are calling it stable?
Yeah, I'm calling it stable in the sense that the solution is not going away from the equilibrium. So the idea of a stable equilibrium is an equilibrium where the solutions are always remaining close to it. If on top of remaining close to it, the solutions are actually moving towards the equilibrium, then we call the equilibrium asymptotically stable. Does that answer your question?
No, I actually don't know that how could I differentiate this. Say if I have a equations, say a set of dynamical equations, and then I solve that, and say after a long period of time my simulation shows that it is approaching to equilibrium, then it's asymptotically stable. But how could I know from the graphical simulation that it is stable? Because in my system I don't know where is the boundary of this B and A thing. This is mathematical definition.
Yes. Yes, in this case, I mean, of course, it depends on the system you are considering, but I would say that you could see if the equilibrium is actually stable by using different initial conditions. So if, I don't know, you guess, for example, from your simulations that X star here has a particular value, you start sampling some solutions around this value. So for example, if we have just to make things simpler, if we are in one dimension, let's say you guess from your simulation that x is more or less equal to 1. Then you could take, you could sample several points around 1. So I don't know, 0.75, 0.80, 0.85, then 1.05, 1.10, and see how these solutions behave. If you see, for example,
like starting from those initial conditions,
yes,
how
exactly.
that.
Exactly. You take like, I don't know, 4, 5, 10 points close to the equilibrium, and you see how the solutions starting from these points behave. If you see, for example, that all of them are going towards the equilibrium, then you have a good indication of the fact that the equilibrium is asymptotically stable.
So going towards the equilibrium means like how long time, or there is no time sense here?
No, in this case, there is no time scale here. I mean, the mathematical requirement is that for t going to infinity, the solutions goes to the equilibrium. So you don't have any kind of measure in this sense.
Oh, then we have always get the asymptotically stable thing. We cannot.
Sorry?
That means we always see the asymptotically stable equilibrium, never the stable equilibrium.
No, it depends. I'm going to show you some examples in this tutorial. But for example, if we have an oscillating system, so for example, if we have, okay, so if we have, for example, I mean, I will show you the Lotka-Volterra system, or for example, a pendulum. So assume this is
excuse me.
Yes.
Leonardo, can you hear me?
Yes, I can hear you.
So, the last slide, can I go back to it?
Yes.
Yeah, so you have written x star is stable not only for all t greater than equal to 0,
yes,
but for all t included in R, right?
Yes.
But time for the sake of its definition, it is supposed to be contained in R plus, right?
Yeah. Yes, I mean, physically, yes, mathematically, not necessarily, meaning that, I mean, if you, let me write it this way, if you have a system like this, so x of t equal to f of x of t, yes, you would say that I can solve this for t greater or larger than 0. But then I could define, I don't know, tau equal to minus t, and solve this system here, x of tau equal to f of x of tau. This is another nonlinear differential equation, which can be solved. But when tau here is larger than 0, t is lower than 0. I don't know if I'm being clear enough. So
it is supposed to be a transformation on t, but t itself cannot be negative.
Yes, if you want, I mean, mathematically, yes. If you want, I can change what I'm saying here by exactly what I've drawn, what I've written here. So if you can say that the equilibrium is stable for t larger than 0, and then it is also stable if you make this change of variables, then it is stable at all times.
Okay, thank you.
Okay, no problem. So about what the question I was answering before. So for example, if we have this is our system, this is our equilibrium. So for example, if we have a solution that goes in circles like this is, for example, what happens for the pendulum equation when we approximate it for very small angles. So you see that in this case, the solution is going around the equilibrium, but is never going close to it or far from it. So in this case, the equilibrium is not asymptotically stable because the solution is not.
Okay. Now I understand. This is the periodic orbit.
Yeah, because the solution is not doing something like that. So the equilibrium is not asymptotically stable, but still the solution is not going away from the equilibrium.
Yes.
Okay, is that clear?
Yep. Thank you.
So.
Just another fact, Leonardo.
Yes.
So actually, in the linear stability analysis, you are always constrained to near about these stable states, stable or unstable states.
Yes.
Never far from it. And then you have to invoke this large deviation, right? So it has
Sorry?
to be always, then you have to invoke, if you far enough, you have to invoke large deviation.
Yes, I mean it depends on the system you're studying, but I'm going to show you show you something about it. But please continue.
So again, all the time, whenever you are applying these analytical results to conclude something, you are
Yes.
again very close enough to your steady states.
Yes.
So this asymptotic stability always matters.
Yes.
Okay.
Yeah,
Thank
I mean
you.
this is also the we can say the price that we have to pay for not being able to solve the equations analytically in general. So of course, if we would be able to solve analytically and nonlinear differential equations, we would be able to say everything globally, basically, about an equilibrium. But since we cannot do that, we have to restrict ourselves to the points of the state space which are close to the equilibrium. Does that answer your question?
Yeah, please go ahead.
Okay, thank you. So I was saying the other side of the coin is instability. So graphically, what happens is what I was saying before. So an equilibrium will be unstable if I can find some initial conditions for which the solutions will eventually go away from the equilibrium. But in this case, go away is the idea of going away is given by neighborhoods. So if there are no further questions, what time is it? Okay, so we still have 10 minutes more or less.
Yes.
More or less. If there are no other questions, okay, I can start introducing Lyapunov functions. So, okay. Now, one of the tools that I have anticipated we can use to study the stability of equilibria in nonlinear system are Lyapunov functions. So let me show you the basic principle that is behind using Lyapunov functions so that the things will be more clear. So let's assume we have a system like this, a nonlinear system, and we know that X star is an equilibrium. Now here I am drawing this in one dimension simply because it's easier, but what I'm saying is true in any number of dimensions. So assume now that we are somehow able, I'm going to explain you how we can be able to do so in a few slides, but assume we are able to define in a neighborhood of this point a function W that has a minimum in X star in the equilibrium. Now, if we had the solutions of the system and we computed the value of this function along the trajectories of the system, for example, we could find out that this function is decreasing along the trajectories. So, for example, we would be in a situation like this. So again, let me repeat, we define this function here in the proximity of an equilibrium. Then we take the trajectories of the system and we compute this function along the trajectories. I'm going to explain you, of course, how we can do that. If, for example, we find out that this function is decreasing along the trajectories, so the time derivative of this function here is negative, then we will be in a situation like this. So you see that necessarily this means that our solutions are moving towards the equilibrium. And this happens because we know that the function here has a minimum in X star. So this would mean in this case that the equilibrium of this system here is asymptotically stable because we know that the solutions are going towards it. On the other hand, if, for example, we find out that this function here is increasing along the trajectory, so if the time derivative of this function is strictly positive, then we are in a situation like this. And so you see that in this case, necessarily the solutions are going away from the equilibrium. So in this case, we could say that this equilibrium is unstable. Is that clear? Okay. So now what I've... yes?
The question by Ngaka.
Hello? Are you approaching from just one side?
Yeah, yeah, of course, I'm showing you just from one side, but I mean, if you flip this image vertically, you see that the same is true also from the other side. If we are in this situation, if you are in this situation, so if the solutions are decreasing, if the value of the function is decreasing, you see that if I started here, let me draw that, probably this will be a little bit clearer. So if this is my situation, this is my equilibrium x star. So let's say that I can define this function here. Let me draw it a little bit better. So you see that if I start here, for example, and I find out that the value of the function is decreasing along the trajectories, then I will have exactly the same situation. So the solution will be approaching the equilibrium from the other side. Does that answer your question?
Yes, yes.
Okay, great. So, okay. So what I've told you now is absolutely non-rigorous. I mean, what I've said, of course, can be made mathematically rigorous. And this is done by what is called the Lyapunov's second theorem. This theorem basically states that if we are exactly in the situation that I have just described, so a general nonlinear system with an equilibrium and this function defined here with a minimum in the equilibrium, then if the time derivative of this function along the trajectories is equal to 0, the theorem says that x star, the equilibrium, will be stable at all times. So if this function here is constant along the trajectories, this equilibrium is stable at all times. On the other hand, if the time derivative is non-positive, so it's either negative or equal to 0, the equilibrium is stable. If it is strictly negative, the equilibrium is asymptotically stable. And if it is strictly positive, the equilibrium is unstable. Finally, a function that I have, a function like this that I have just introduced is simply called the Lyapunov function for this equilibrium. Now, we still have 5 minutes, 10 minutes, more or less.
It's about 10 minutes. So
Okay.
perhaps we can see if there are more questions from the
Absolutely.
audience. I mean, it depends on whether, because Leonardo is giving a second part of this tutorial tomorrow. So it also depends, Leonardo, on whether you want to, how you want to divide it into parts. But I will say, let's see if...
absolutely. I can stop here, no problem.
Okay. So are there questions, clarifications, something that is unclear?
So I have one question.
Yes.
Yes, please.
My question is that in this case, the equilibrium is the minimum. Is this property still true for when we have an equilibrium which is a maximum?
Yes, I mean, you could write basically the same exact theorem when the function has a maximum in the equilibrium instead of a minimum. Of course, you would have to change the names here because of course, if here we have a function with a minimum in the equilibrium and we find, for example, that the time derivative is negative, then we are moving. Let me draw this. Sorry, probably this will be more clear. So what I've just told you in the slides is basically that if we are in this situation, so I have my equilibrium and I have this function here with a minimum. So what I've shown you in this case is that if the function decreases along the trajectories, then we are moving towards the equilibrium. So the equilibrium is asymptotically stable. But for example, if we decided to define the function differently, so instead of having a minimum in the equilibrium, it had a maximum. Okay, so the situation looks a little bit like this. You see that the equilibrium in this case would be asymptotically stable only if the value of the function increases along the trajectories. Because in this case, we would have that the function is increasing like this, and so we are actually moving towards the equilibrium. So yes, we could very well do the exact same thing with a function that has a maximum on the equilibrium, provided that we change the definitions here accordingly. Is that clear?
Mohammad, is clear the question, the answer?
Yeah, it is clear. It is clear.
Then there is a question from Juan Jose. Please unmute yourself.
Yes, thank you. I wanted to ask you if when we are looking for an attractor of a chaotic system, is there around those trajectories that are closed in a kind of space near the equilibrium points? There, are we talking about the same notion of equilibrium, or it's a bit different?
You know, it's I would say that it is similar, but the notion of attractor is actually wider, let's say, than simple equilibrium, because by equilibrium we mean a point, a specific point in the state space, while an attractor can be something more. I mean, it can be also a different set, because, for example, I don't know if you have ever heard of limit cycles, sorry, but there are some dynamical systems, for example, where we find out that there is, I mean, I'm just showing an example, there is, for example, this circumference, and any solution that starts, for example, here, instead of tending towards a particular point, it will tend towards this trajectory. So the solution will do something like this. Sorry, I am terrible at drawing, but the idea is that the solution, instead of going towards a particular point, it goes towards a trajectory. Now, the intuitive idea is the same. So if we have that the solution instead of tending towards a point, it tends towards a trajectory, I mean, the idea is the same, but mathematically these things are very different, and there is a whole different set of tools that can be used to study them.
Oh, thank you very much.
No problem.
The second in line for asking a question was Ayan. Ryan?
Yeah, I can hear you.
Yes, yes, I can hear you.
So I was just wondering, if we go back from dynamical systems theory to study ecological networks, the concept of equilibrium and steady state. So non-equilibrium is something when you have this exchange of energy, right?
Yes.
So then, which I guess is always the case in ecological networks. So the proper terminology over there maybe is to use steady states or unstable steady states rather than using these equilibrium states.
Yes, when we talk about thermodynamically open systems, let's say, so systems where there is an input of matter or energy or any kind of thermodynamic quantities like ecosystems, technically we should say steady states and not really equilibrium, because there is no equilibrium. Yes, so you are right.
Thank you.
Okay, there was another question by Pablo Lechon.
Hello. So, but when you're talking about not being able to solve the linear system, and then in order for you to talk about stability, you have to talk about stability in a region near equilibrium.
Yes.
Why is that? Is that because if you don't know how to solve the system, would you linearize it around the equilibrium, or?
Yes, exactly. I mean, if you don't, I mean, if we would know the full analytical solution, like in the case I've shown you a few slides ago on the logistic equation, so if we could find the analytic solution like this here, we could say anything that we can say about the system. We have like the maximum information possible on the system. But when this is not possible, and this is not possible almost always, basically, we have to find ways to determine the maximal information, which necessarily cannot be the maximum information, because we cannot solve the system. So we have to do our best, and often doing our best is studying the system close to equilibria. Did that answer your question?
Yes, thank you.
No problem.
Great. Next in line is Debasmita.
Can you hear me?
Yes.
Hello. Yeah. So my question is that construction of this Lyapunov function, like whenever we change the model, so there I face problem with construction of Lyapunov function. So can you suggest some techniques that some base techniques to assume what kind of Lyapunov function we can assume for to test the stability of a particular system?
Sorry, I lost the audio for a moment. Can you repeat the question?
Yeah, so I'm asking about construction of the Lyapunov function for any system.
Yeah, I mean, this is the great problem of this approach. I mean, as you can see, it's actually very powerful because it can tell us a lot about an equilibrium, but the problem of this approach is exactly building a Lyapunov function. In general, it is not easy at all to find the Lyapunov function for any generic system. So we have to be either lucky or we have to use some intuition to build the Lyapunov function. So there is always this kind of trade-off. So we have a very powerful tool, but this powerful tool is not easy to use and it's not possible to use it always.
Okay. Thank you.
Then there was, okay. Sorry, you were saying something? There was Mita?
Yeah, it's fine.
So then there was a question by Samson Olaini.
All right. Thank you very much for giving me opportunity to ask my question. First of all, I want to appreciate the presenter for this wonderful presentation.
Thank you.
My question goes straight like this. When can we have a situation of global asymptotic stability?
Mm-hmm. Sorry, I don't think I heard correctly because of some audio problems. What was your question?
I'm talking about, my question is tending towards when are you going to have a situation of global asymptotic stability?
Oh, well, it depends. A case when we can say globally that an equilibrium is asymptotically stable, for example, are systems with conserved quantities. For example, if we have a particle in a potential, so a very simple physical system, this particle can move only on the x-axis, and we know that this is subject to a given potential, energy potential V. And for example, we know that this potential, for example, is a parabola. So this is defined on all the x-axis. So we know globally how the potential work. We know that, I mean, from physics, we know that the equilibrium, the equilibria of this system are the minima of the energy potential. So in this case, since this is a parabola, we only have a minimum. And so in this case, we can say, okay, there is one asymptotically stable equilibrium, and this is the only one that there is in the system. So, I mean, this is a lucky case in which we can tell anything about the system globally and not only locally. Did that answer my question?
Oh,
your question.
Thank you.
Yes?
I think
you're right. I'm satisfied.
Oh, okay, thank you.
So there was okay. So there is a question which is quite popular in the chat, and I think could be the last question of today's session. So the question is there any general principle guiding us to the construction of a Lyapunov function?
No, this is the great problem of this approach. There is no general principle. We have to be lucky or smart. I mean, there is one big exception. I'm going to talk about this tomorrow, but if we know, for example, that we have a system with a conserved quantity, so if we, for any reason, know that there is, like I've shown you before, potential energy or any kind of quantity that is conserved, generally, these conserved quantities are a good first guess for a Lyapunov function. This is not always true. We have, every time we have to check that they are good Lyapunov functions, but generally, when we have conserved quantities, these are good. These can be good Lyapunov functions. If we don't have conserved quantities, then we are completely on our own, and we have to find them on our own, which can be difficult or even outright impossible in some cases.
Okay, great. So I would say that this is the perfectly on time, the end of the today's session, today's tutorial. So as a reminder, Leonardo will give the second part of this tutorial tomorrow at the same time. So you can also watch again 2 or 3 times, I mean, as many times as you want, the tutorial that Leonardo gave today on YouTube. So if you want to, you miss something and you want to watch it again, please do. So the next slot in the next lecture by Joshua White is starting in about 13 minutes. So what we're going to do now is to split in randomly assigned breaking rooms. You are free to stay in the breaking rooms, chat with whoever you are assigned randomly to. You should be able to switch the breaking rooms to switch a room if you see someone you want to say hi. I guess Leonardo is staying with us, so you can also
yes, absolutely
question more informally. And but also you are free, of course, to stretch your legs, to get a cup of coffee, or take a break from the video. So with that, since I'm not host,
I'm ready.
Okay. Yes, I give you. Please.
Here we go.
Yes.
Okay. 20 breakout rooms. Is it okay?
Yes. Okay.
Because 150 people.
Yes. Sounds good.
Okay.
Can someone on the ICTP side, if you can hear me, let me know?
Yes, I have answered you in the chat. So your sharing is good.
Okay.
I can see your sharing very good. So it's okay. I just remember you that remind that we are now live on streaming.
Yeah, no, I understand.
Okay.
On streaming.
That's
Hello,
all.
streaming people.
Yeah, perfectly.
Great.
Hey, Josh. Can you hear me? Hi.
Yes, I can hear you.
Oh, great. Okay, so I was, because we have the participants paired randomly randomly in meeting groups, so I was in one of those.
Okay, that's
but I was
fine.
trying to find you. So how is it going?
It's going fine. You have a big crowd. I think we're live on streaming, so
okay.
Yeah, just keep that in mind. Hello,
Okay.
everyone who's watching us have this chit chat.
I see. Okay, great.
Yeah. If you want to discuss anything before we start, we can go to a breakout room, but otherwise, I think I'm set. And
Yeah, I leave with your coffee. I think you checked everything. Okay, great. Thanks. Okay, everyone, we are about to close the rooms and start with the lectures again. So in a couple of seconds, all the breaking rooms will be closed and people will join again the main meeting. Okay, in about 1 minute, I'll start introducing the next lecturer, so then people have time to join back. Okay, great. So I think we can start with the next slot. So the next lecturer is Joshua Weitz, who is my pleasure to introduce. Joshua is a professor at the School of Biological Sciences and Physics at Georgia Tech in the United States. He's an interdisciplinary researcher with a very broad range of interests and perspectives in mainly in theoretical ecology and quantitative biology. Most of his recent research is focused on bacteriophage interactions and dynamics at multiple scales, from the fine-scale microscopic details of this interaction to its ecosystem large-scale consequences. So today, Joshua Weitz is giving the first lecture of three. Sorry, there is. Can you hear me? Can I?
Yes, I can hear you.
Okay.
I'm giving one of three lectures.
Great. Okay. Because I received comments in the chat. So great. So today is giving the first of three lectures of virus microdynamics. So please, Joshua, thank you very much for giving these three lectures. Please share the screen. And let me remind the audience, if you have a question, please use the raise hand button that you can find under participants of Zoom. And I'll give you the possibility to talk.
Okay, great. Can you hear me, Jacopo?
Yes, perfect.
Okay, wonderful. Thanks for the invitation. Welcome to the many 100 plus, not 200 plus, that are here joining internationally. I just have a few preliminary slides before I get started. First of all, just to let folks know that I'm also the founding director of a quantitative biosciences graduate program at Georgia Tech. We are accepting applications now to for entry in fall 2021 at qbios.gatech.edu. And if you want more info, again, go to the website. We have cohorts of approximately 8 folks per year, looking to welcome a new cohort in the coming year. And just a bit about our group. Again, we're located in the United States, the Southeast United States, the state of Georgia. And that gives you some indication of the team. Folks come from all over the world, much like in this meeting, to work on problems related to virus microdynamics and theoretical ecology, evolutionary biology, quantitative biosciences more generally. As Jacopo mentioned, I'll be giving one of 3 lectures. I recognize the background here is quite broad, so I'll try to use today's lecture as an opportunity to set a foundation. It may cover more material than is humanly possible in this hour, but I will try. And if it goes too fast, I'm under the impression that A, this is being recorded and it can be reshared, and also that the slides will be made available so you can review them at your leisure. And again, this is collaborative work, and I'll try to go over a number of different topics supported by the National Science Foundation, NIH, Army Research Office, Simons Foundation, and others. Okay, so to get started, I'll try to start with a boring slide, visually at least, and although it looks boring to look at, I'm going to claim that this is actually a fascinating experiment. Some of you may be familiar with it. You can see here in the rows, you have these experiment numbers, and these are replica of the same experiment. As you can see, there's a lot of variability across the different experiments, and I'll just only give the hint that these have something to do with counting bacterial colonies. And if any of you have ever done experiments with bacterial growth, you would probably imagine that you don't want to report back the results of an experiment where sometimes you got no colonies, sometimes 303 and 48 and 3, totally unpredictable. Okay? But yet this experiment, as I'll explain in a moment, sits at the very heart of how we think of virus microbe dynamics. In fact, really influences all of modern biology. I'll give just one example of this particular experiment, number 5, where you see this incredible variability, sometimes no colonies, sometimes 100 plus, extreme variability. Now, what this actually was is the number of colonies that were resistant to the action of a particular phage. And so this tells us something about the emergence of resistance in a population. And it comes from this paper that many of you know by Lurie and Delbruck on mutations from susceptibility to resistance against viruses. And it comes directly here, that one that I highlighted here from experiment number 16. And Lurie and Delbruck, along with Chase, won the Nobel Prize in 1969, in large part due to the understanding and advances that they were able to push ahead using this experimental setup. Now, to understand a little bit more, at the time, we have to go back in time and think a little bit about the differences between what people thought might be the basis for the emergence of viral resistance within bacteria. It could be dependent on selection or independent of selection. Really, mutations more generally, it was not necessarily clear which way these things work. Was it Darwinian in some sense or Lamarckian in another sense? So we can imagine for a moment, as a thought experiment, the growth of a bacterial population from a single ancestor, where you can see these are all susceptible, they're denoted as clear, they're dividing over time until after a certain number of generations, log 2 of n, the final size of the population, we have this entirely susceptible population, which is then exposed to viruses that should presumably infect and lyse all of these bacteria, except through a acquisition mechanism if resistance is dependent upon interaction with the virus. In other words, selection mutations are dependent on selection, then the subset of these will survive viral infection, but in some sense like a Poisson experiment, Poisson distribution, meaning there's some random chance per bacteria. And if we do this again, we'll get a small number, repeatedly a relatively small number of colonies that will have this particular phenotypic trait. Alternatively, it could be that mutations are independent rather than dependent on selection, and therefore early in the proliferation process, even before viruses were added, a subpopulation had a mutation which were then resistant to viruses. Only then were revealed when you actually expose them, and then a large number of these bacteria, again, which were already present, survived viral infection. And that large number really depends on how far back in time, how many generations ago this mutation occurred and then proliferated. And in light of this, one expects actually that in this context, you should have significant variability. The earlier these mutations occurred, the more they may be in the final event. And the later they occurred, the smaller, even none at all. And this is precisely revealed here where I look at the number of mutants. This is a Poisson fit. Obviously, it's not a good fit. This is the number of cultures with this number of mutants. And you can see this long tail effect, right? Where you can see that in some cases, you get these rare jackpot-like events in which there's a number of these cultures that have many mutants, whereas this is just certainly not expected in the Poisson case. Okay? So this table that looks visually quite boring actually tells a very important Nobel Prize winning story, which is that mutations are independent of selection, at least in general, and we can talk about CRISPR-Cas some other point maybe in the chat. So the takeaway from this in the early 1940s that viruses impose a strong selection pressure. Host mutations that confer resistance are beneficial. In some fundamental sense, then viruses induced host evolution, right? We have a change in the frequency of genotypes in a population that is induced by the actions of this viral selection pressure. But what about the viruses? So this famous paper by Lurie and Delbruck is not often seen from the other side, right? Which is viruses are a convenient way to impose a selection pressure. But what do the viruses do? In fact, in a later work, Lurie explored this question by looking at the inducement of resistance amongst bacteria against phage, but also then counter defenses, in some ways niche expansion by phage against bacteria. And here the squares denote the phage, these circular oval-like things denote the bacteria. And what you can see through the solid lines are the intrinsic ability of this particular phage to infect and lyse particular strains of bacteria. And you'll notice the absence of such lines in other cases where these host range expansion mutants of phage can infect not only the ancestral types, but also these newly evolved types. So in some sense, we have the host range of viruses expanding, you can see here twice. And then eventually in these experiments, a phage-resistant host range emerged. So yes, not only can bacteria induce evolution in phage and vice versa, but at least in these early experiments, there was a notion of coevolution, but there was a sense that this interaction might get short-circuited. In fact, really, this dogma persisted for decades. And this dogma is encapsulated by this idea: the coevolutionary potential of virulent phage is less than that of the bacterial host back in the mid-80s. And part of this was also informed by the fact that it just seemed very hard to find abundant bacteriophage in natural systems. And maybe that was yet another indication that the bacteria kept escaping their phage parasites. But then something happened. And what happened was, a few years later in the late 80s, a group looking at aquatic systems began to take a culture-independent approach to try to assay the abundance of viruses in natural systems by taking water samples here from a lake. They were also doing this in marine systems, and then staining anything that seemed to contain genetic material, DNA. And then if you see these arrows, counting the number of these small dots, because here's a scale of 1 micron, these things seem to be about 50 nanometers to 100 nanometers in size, and there were a lot of them. And they went back through and counted how many of these virus-like particles there were in these particular systems, back inferred based on the dilution to the abundance of viruses, and found that there were 250 million virus particles per milliliter in natural waters, 1,000 to 10 million times higher than previous reports, right? So this is just an incredible difference. And part of this because previous reports were using a host, and almost certainly the wrong host for the bulk of these viruses, as a means to count by looking for plaques in the same way that Lurie and Delbruck looked. But if we don't know the host, and we certainly don't know the virus, and we may undercount. So there was some sense in the late 80s, and this is really the jumpstart of this new approach and new really ecological orientation to thinking hard about virus microbe dynamics in environmental systems. And it was then realized about a decade later that not only were there a lot of viruses and they could infect and lyse particular bacteria, but they also had a role in the ecosystem, because as viruses infected and lyse bacteria, they could redirect organic material, this DOM, dissolved organic material, back into the ecosystem. So again, there was a notion not only were viruses interesting from their perspective potentially as agents of mortality, but also in their role in shaping ecosystems. And you can see that here. Again, they divert the flow of carbon and nutrients, releasing the contents of cells back into this DOM pool. And of course, there were a lot of viruses. And part of the challenge is once you have 10 million or 100 million per milliliter, these are all not the same type. These are not monolithic, it's not a monoculture. And from the outset, and this hasn't changed that much, although there's been improvements in understanding viral types, the vast majority of these were basically unknown to science. So the majority of these were uncharacterized. Much of the diversity in the early 2000s was uncharacterized. And obviously that's been improved quite significantly since then. So what do we talk about when we talk about viruses? I would say in normal times, we might talk about viruses that infect humans, whether it's Ebola, Zika, or influenza. And obviously right now I'm giving, and I'm aware that I am giving a lecture about virus dynamics when most people are just thinking about this, right? SARS-CoV-2. And yet I won't be talking about that today or in the next few lectures. I'm looking forward to this break and talking about something else, some other exciting stuff that we're doing in the group. But just to point out that yes, over the past year, we have been working on COVID-19 quite extensively, as I'm sure many of you have in all sorts of ways, including what you see in the upper right is some of our collective work to develop asymptomatic surveillance system at Georgia Tech, which is available to anyone, students, staff, faculty, on a weekly basis. People sometimes test more than once a week, saliva-based PCR tests, and you see we had an outbreak but detected it very quickly, and we're able to maintain, with this one exception, but again, we're able to contain that very quickly, rates of positive incidence less than 1% based on these population level sampling over the course of the fall term. We've also worked on other dynamic models, including some work developing a COVID-19 event risk assessment, and there's an Italian version that some of you may be aware of. It's received multiple millions of views since we launched, and happy to discuss that some other time. Okay, but viruses do, as you know, infect organisms across the diversity of life. And also just to point out, I believe there is going to be one set of speakers who is going to talk about models of COVID-19 later in this, and there'll also be a forum. So you will get a chance to learn more about these sort of class of models and infectious disease models by a few speakers later on. But viruses do infect organisms across the diversity of life, not only charismatic humans, mammals, birds, etc., but also microbes, including eukaryotes, as well as archaea and bacteria. And just to give you some indication that these viruses can also be somewhat charismatic as well. Here are some images, at least, of the virus particles. And the bulk of the work looking at virus microdynamics often goes through the same paradigm as Lurie and Delbruck, which is to think about viruses as agents of mortality. Here are three particular examples where I'm showing what happens when you have a culture alone, EHUX, algae, and here is Prochlorococcus Marinus med4, ubiquitous cyanobacteria found in the open oceans at high densities globally, in the surface oceans. And then here are examples of what happens when you add viruses. And you can see the decay in density and the increase in viruses. In this last case, actually was timing of looking at the decline of host DNA as well as the intracellular and extracellular development of phage DNA. So the takeaway here is that viruses act at these microscopic scales across a diverse set of hosts to infect and lyse, reducing the density of the host, increasing their own density over time. You can learn more about this generally in this very nice popular book, and this goes well beyond viruses of microbes by Carl Zimmer. It's called A Planet of Viruses, and you will find that would be a nice evening read. It really spans the scale from oceans. This is a not to scale pictorial of a cyanophage right here on the surface, on the cover. It made the cover, but also viruses of humans and so on. And this will not be an easy bedtime read, but if you're really interested and you get inspired and want to learn more, I've also written a book called Quantitative Viral Ecology. It's meant to be a graduate level, intro graduate level textbook, but it also can be a guide, Dynamics of Viruses and Their Microbial Hosts. It was published in late 2015. Okay, so what am I going to do in these three lectures with this introductory material in mind? Today, I'm going to try to go through, as I said, principles of ecoevolutionary dynamics, trying to give folks an idea of some of these core ideas of how we can think about virus microdynamics and begin to think at multiple scales, connecting microscopic mechanisms to emergent population dynamics, and hint at least a little bit at some of the ecosystem consequences. But in the interest of time, I won't get into that as much as I've done in some other contexts. In the second lecture, I will try to extend the scope beyond what I will do today, which is largely a predator-prey paradigm, and then talk more about parasite-host paradigms. And of course, we know phage are parasites, but using the language and context and thinking of epidemiology may take us in some new directions. So I will do that tomorrow. And then on Thursday, I will connect some of these principles to applications, and I will choose just one. Rather than on an ecosystem context, I will choose a biomedical health context and begin to show efforts to use phage as therapeutics and explain, in my view, why thinking about virus microdynamics, again, as a dynamical system, may actually aid in efforts to treat multi-drug resistant bacterial infections. So that's what I'll try to do today. Principles. Tomorrow, expand these principles into some new directions. And on Thursday, go towards therapy. And Jacopo, you'll let me know if anything goes wrong, but otherwise I'm gonna keep plunging ahead.
Absolutely. I'll also let you know if there are questions or changes. Okay, great.
That's perfect. And again, throughout, I will try to connect theory and modeling with both fundamental challenges as well as real world applications, as you can see. And obviously this will build towards these real world applications even further as we get to the focus on Thursday. Okay, so again, principles today, more on principles really on the switch between lysis and latency tomorrow, and Thursday connecting theory to therapy. Good.
So there is a question actually from Ian. So Ian, please unmute yourself.
Yeah. Am I audible?
You are. I can hear you.
Yeah. So Professor Witz, I was just wondering from the Luria-Delbruck perspective. So you have a Poissonian dynamics coming in. So I was just wondering, if you have a larger amount of population of these viruses, do they actually try to get in the CLT, that is like a central limit theorem, and get it to like a normal distribution or so? And I'm just asking this question from a perspective of gene transcription regulation dynamics. So when you have this unregulated dynamics of some transcription factors, you have this Poissonian dynamics coming in. But whenever it's something it's getting regulated by a transcription factor, you go away from this Poissonian dynamics mostly.
Right.
So is there something similar?
Yeah. So thank you for the question. As you can see here, you brought up a number of different ideas. There are certainly notions in which the viral takeover of a cell can be described through the process of stochastic gene regulation, just as we can think of a cell's dynamics as through that process. And if we have some unregulated gene, then notions of a Poisson-like distribution of transcripts and even proteins can emerge, and certainly in certain limits that can look Gaussian. But that really is beyond the scope. We don't need to invoke that to understand the fact that what we're looking here is at outcome. And if resistance here has a largely to do with surface resistance, so the viruses aren't even getting in, then we don't need to ascribe all the processes that could be interesting to explore in some other context. But we could just think of it as the outcome of those cells, those colonies didn't even enable or permit the viruses to get inside. We could have a separate discussion on intracellular resistance, whether resistance modification mechanism or CRISPR-Cas immunity, and that would turn out different. And we might need to think about gene regulation there, and we certainly have done in other contexts. So hopefully that helps. This is strictly the colonies are resistant. We don't necessarily need to invoke the details, the intracellular details, to understand that then that colony, its offspring, inherit that same feature of being resistant, and that's why we get a Poisson distribution at the level of resistant colonies. Okay,
thank you.
Good. Why don't I keep moving ahead, Jacopo? Is that good?
Yeah.
Great. Okay, so what I'll try to do today is explain a few things, and I will essentially give you an introduction to how viral infection can change microbial population dynamics, but you've already seen that we can't stop at population dynamics. We have to think about evolutionary change. So I will then go in that direction. And then we'll see how far I go. I have about 35 minutes. I'm going to try to use it all to really give you this broad introduction and expand some of this in the direction of virus host dynamics in complex communities. Okay, so how does viral infection change microbial population dynamics? Well, to do that, and again, since I have I'm lucky to be here at the early start of this thing, and you've just had one introductory lecture, and I'm sure many of you heard of Volterra. And a long time ago, Vito Volterra, and it's always fun to say that name when we're here in a Trieste Italian conference, was convinced by his son-in-law, Umberto d'Ancona, to examine fluctuations of the Adriatic fisheries. Why is it that we see these fluctuations? Is this all exogenously driven, or can there be the result of endogenous interaction? And the first case that Volterra considered was of two associated species. One would multiply indefinitely because it would just keep growing, but the other one would die if it was left alone. But the second one, the predator feeds on the first, the prey, and the two species can coexist together. In modern language, we would write down the model that Volterra and then Alfred Locke independently proposed as a coupled system of nonlinear differential equations, where the dot denotes the derivative. Here we have the indefinite proliferation. Here we have predation, conversion of prey biomass into predator biomass, and the death of this predator if left alone. The outcome of this are these predator-prey oscillations where the predator peaks tend to be shifted to the right of prey peaks. So we have a prey peak, then predators rise in abundance, driving down prey. As prey are driven down, then predators decline, prey go back up again, and we see the cycle continues. We could then superimpose this on a prey-predator phase plane and note that we get these cycles, and they're counterclockwise. And the reason they're counterclockwise is, again, we have a prey peak, which leads to the rise of predators. The rise of predators leads to the decline of prey, and the decline of prey leads to the decline of predators, allowing prey to restore, and so on. You will notice that this seems to be a closed orbit. That is true, which means that if you had a different initial condition, you'd have a different closed orbit, which in physics would be terrific news. We'd have a conservative system. But that is not good news for biology, because it means that the initial condition is remembered forever. These are not true limit cycles. So just keep that in mind as a caution. Of course, later models did have true limit cycles, and that was often because there was some handling time or other features of the interactions, again, which is that prey peaks before the predators, they're lagged, and then the oscillations again appear counterclockwise in the prey-predator phase plane, as you can see here on the right. These ideas of Lacan and Volterra really sit at the heart of how the field of virus microdynamics has emerged, beginning in work by Bruce Levin in the late 1970s, along with Frank Stewart, mathematician, and Lin Chow. Bruce is now here at Emory, and Lin is at University of California, San Diego. And in their view, they viewed this system, an experimental system of having a phage, a bacteria, and something for the bacteria to eat on, as a resource, a prey, the bacteria, and a predator, the virus. And the idea really goes back even to Alan Campbell in the 60s, that these phage, these viruses that exclusively infect and lyse bacteria, we can think of them as a simple predator. And the reason or rationale is that they act to convert prey biomass into predator biomass, and also they never lead to the death of the prey through that process. Okay? So this Lacan-Volterra model in a more simplified form, again, is the basis for these virus host population dynamic models. And here again, you can see this simple resource prey predator model. And this is a model in which we're envisioning a chemostat in which there's a rate omega in which resources are flowed into the system, and a rate omega at which everything is flowed out, including resources, prey, and predators, the bacteria and the viruses. The prey take up resources, converting it into new prey. The viruses infect and lyse bacteria, leading to beta, this burst size of new viruses. And what you can see is that if you start a in silico chemostat with a certain number of prey and resources and add a virus, you get oscillations, you get a decline, excuse me, in prey density, because now it's being top down rather than bottom up controlled. And you also see these oscillations. Although it's hard to see here in this log space, we can project this onto the phase plane, ignoring the resource level. And what we see are these counterclockwise dynamics, right? And the counterclockwise dynamics are for the same reason that we have these Lacan-Volterra-like dynamics, that we have a peak and viruses driving down the host density, leading to a decay in the viral density, allowing to the restoration of prey density, and so on. In this particular set of equations, this should actually relax back to an equilibrium to a fixed point. So just to remind everyone so that we're on the same page, this is a bit of the life history of a bacterial virus. I'll go through this probably once in each lecture just to make sure everyone remembers. And in case you showed up for one, I'll probably do it again, but also do it a little bit faster each time, because I'll assume you will have remembered it. Here we have this 50 to 100 nanometer size passive bacteriophage. It's diffusing in natural environment, comes into contact with the bacterial host, injects its genetic material into the bacterial host, takes over the cell machinery, as was alluded to by Ayan, and then through a time process leads to both the encapsulation of the genetic material into the capsid of the host, the self-assembly of these, of the virus, the self-assembly of these viruses, and through the release of both whole and lysine genes, there can be a hole made in the inner membrane, a hole made in the cell wall, and out go the viruses, and the life cycle continues. Okay, so this is just a process by which a parasite takes over a host, a microbial host, and you can see there's a time that it will take between when this happens and when this happens, right? Between adsorption, encounter, infection, injection, etc., and lysis. And so obviously the earlier model didn't have this. There was an assumption of an immediate conversion of prey, bacterial density, biomass into that of the virus. So obviously we need to make some corrections there. And this is all done in a particular context, right? This chemostat context in which we're envisioning that media is being flowed in. There's some dynamics here, but everything is going out through waste, which we can then measure and observe. So these types of models can also be extended to include models with an infected class. And the point I'm showing here, for those of you familiar with reading these, is this susceptible host, infected host, and viruses. The only difference is that rather than immediate lysis, now we have an infected class which decays at a rate eta. So in other words, 1/8 is the latent period, and we get new viruses. The point is that in this model, we get a true limit cycle. Again, counterclockwise dynamics, but leading to a true limit cycle. You might not like that because you might say, well, a rate eta of decay means that we have an exponentially distributed distribution of latent periods, and the peak of such a distribution is at 0, and that's too soon. We could also make an explicit delayed set of differential equations in which the infected bacteria are produced at a rate phi and v, but then this subscript tau means the number of bacteria and viruses tau before are those that are released now. These become more complicated to deal with for various reasons. As you can see, you instead of having a finite number of initial conditions, here you need an infinite number of initial conditions because you have to go back in all the times between 0 and negative tau. There's also this decay because some of the bacteria that were infected before, not all of them survive because some of them are being washed out through the chemostat, which is why we have this e to the minus omega tau factor. Nonetheless, in this particular model, the quantitative details may differ a little bit, but the qualitative features remain. We again get these counterclockwise dynamics. So we have this robustness of an idea from Locke-Volterra that could be applied to virus microbe dynamics, which is the same notion of a simple predator-prey system should lead to endogenous oscillations of this counterclockwise type. And just to put a little mathematical checkpoint here, as I assume that you're going through in these nonlinear dynamic tutorials, that it's not inevitable just because a virus can infect a host that it can invade, but rather we need to think of this as in some ways a destabilization of a otherwise stable fixed point, which we just have bacteria. And so you need to look at most simply the linearized system and check to see if the eigenvalue was positive, and that would imply invasion. I go over this in the book, and on Tuesday's lecture, I actually elaborate on intuitive criteria that can explain this as well. Okay, so just to remind folks that it's not inevitable, not every virus, just because it infected bacteria, the ecological conditions have to be sufficient, which depend on life history traits as well as the abundance of the host. So just, can I finish this thought, or you had a question, Jacopo?
There is a question from the audience. If you want to go on, you prefer, you can wait, otherwise.
Let me just finish this one side, few more slides, and then I'll take the question. Just because I don't want to lose the train of thought here, which is these same types of dynamics can be observed in the laboratory. These are Locke-Volterra-like cycles between phage T4 and E. coli B. You can see the population density time. So this is about a 10-day experiment where we have large-scale endogenous oscillations. And you can see that the ratio of virus to the host can be quite large, on the order of hundreds, if not thousands. There's also a time shift here, so that when the bacteria peaks, it's usually followed by the virus peak. And again, this is in a chemostat system where it's otherwise homogeneous, shaken, and not being driven by some exogenous change in resources. So just to point out here that this really is a demonstration that there can be a feedback between virus and host that lead to endogenous oscillations. That's why I just wanted to get this one idea out, then I'll take the question. These original models of virus-host dynamics presuppose a simple one virus, one host relationship. If viruses act like predators, we should expect cyclical dynamics, whether we use these simple Locke-Volterra-like models or ones that take into account the microscopic details of infection and lysis. and reminding folks that invasion is not inevitable. It depends on traits, and this has been observed in experimental systems. So this would be a good time to take a question.
Yeah, thanks. I just had a very quick question. A few slides ago, when you were talking about the delays and you had this n sub tau, can you just, you went quickly over that. Can you just say again, what is tau, and are you integrating over tau in that equation? Or
right, so tau is a fixed latent period. So
okay.
you should think of this as n of t minus tau. So this is interpreting this would say that the change in the number of infected cells now is equal to new infections minus infectants that happened tau ago that are now lysing.
Good. And when you say an infinite number of initial conditions, you just mean you have to keep track of tau's worth of time data to be able to run.
Correct. And so just to point out for people who are not so used to it, that it's just a different way of thinking about this particular system. And oftentimes what people do, if they don't want to do with delay differential equations, is to set up a finite number of stages which replicate these kind of shapes of distributions, and then you can go back to this ordinary differential equation approach.
Good. And is the set of solutions to that differential equation really an infinite dimensional parameter space, or I mean, is it really different for? I guess it's different for every n tau function.
So just keep in mind, remember, n tau is not a function. That's just n of t minus tau. So you're getting one set of NIV solutions, but to figure out what happens now, you need to go back tau ago. So just because of that delay.
Right, but the initial conditions would have n as a function of tau for that period of time.
N of t between 0 and minus tau ago in order to integrate forward.
Thanks a lot.
Yep. Great. We're good, Jacobo?
Yes.
I'm plunging ahead. Here I go. Part 2. But I'm on pace. I'm gonna finish. So I've set things up here intentionally. So we have ecological dynamics, but I've already told you, Lurie and Delbruck told us that we should expect evolution, if not coevolutionary change. So I'll try to give some sense of this question: how does coevolutionary change and evolutionary change affect these population dynamics? So let me go back now to this experiment which I showed you, in which we have these endogenous oscillations, Locke-Volterra-like oscillations between viruses and E. coli. And what I want to now show is something different, and I'll switch back between them, which is that for the first 200 hours or so, it all looked like theory was fine and we'd be done. But past that time, something else happened. This is the same chemostat, but now we see essentially a flat line of hosts and oscillations of viruses. And given the size of this crowd and the context, I'll just point out that the fact that viruses are increasing implies this is a chemostat they would otherwise decay. They're replicating on something. But what's interesting here is that the host density remains apparently flat, which doesn't seem to make sense. If you saw this time series and this time series, you wouldn't necessarily relate them. And this is why this is often called cryptic dynamics. What happened, in fact, is that they went and observed that this host population was not homogeneous anymore, but in fact was comprised of two different populations, one that seemed more susceptible and resistant to the virus. They isolated it, marked those, and then were able to repeat the experiment in some sense by being able to track the two types independently. And what they found is that what happened was that there was the emergence of resistance. So a subpopulation was resistant, rose to a high abundance, but there was still a susceptible subpopulation that viruses were replicating on this subpopulation. And if you'll notice, these dynamics look Locke-Volterra-like between the virus and the susceptible host in terms of being phase shifted, but also these susceptible host oscillations, note the log scale, would just be noise in the background of the resistant host density, implying that we do have the emergence of resistance, and there's essentially an evolution of the system in which the viruses have induced evolution, but not leading to their own extinction, but rather than to a new kind of dynamic. So again, just to point out that these resistant hosts invade, obviously they have that benefit, but they don't exclude the susceptible host because they come with somewhat of a cost. And if there is a trade-off between growth and resistance or defense, then these two different types can coexist. Which leads me to a more general point, which is that when you have predator-prey-like dynamics in a virus microbe system, you can get these canonical predator-prey cycles, Locke-Volterra cycles. When you have evolution, you can get cryptic cycles or antiphase dynamics, and that's a more general problem in the field of rapid ecoevolutionary dynamics, and has been seen notably in other predator-prey systems, including that of rotifers. And we also have a multi-type possibility as well. So this is no evolution. Evolution, I'm about to explain why something even funkier can occur, where it seems like the prey peak is following the predator peak. In other words, prey eating predators, not the case, but something about this system has fundamentally changed when there can be coevolutionary dynamics. And just to make this more explicit, here I've taken a system now of 2 viruses and 2 hosts. So we have coevolution in the sense that there's the change of the frequency of genotypes in a population over time. You can see the shading here. These dashed lines denote the virus strains, and the darker lines denote the host strains. And when you add them together, the total virus and total host seem to have a predator-prey-like dynamic, but shifted, where the virus peak precedes the host peak. Okay, so I hope that's clear. You can see also this in a phase plane, where when you get one of these clockwise cycles, what this implies is that rather going around this way, it goes around this way, which is not what we expect, because it means that the peak in predators is then followed by an increase in prey. And we can understand this by recognizing that at the same time the total population is changing, we also have changes in the fraction and the frequencies of genotypes, here hosts and here viruses. And I've denoted them by having these high vulnerability types and these low vulnerability, you know, there's defense specialists. And then we also have viruses that may have low offensive types and high offensive types in terms of being able to get in more efficiently and otherwise not, but they differ in their decay rates between the types. And what you can see here as at the peak of the system from the perspective of predators, we have a lot of high vulnerability types, which leads to an opportunity for these low offense types to invade. But as these low offense types invade on the viruses, then the system can shift to low vulnerability, and these low vulnerability hosts can do exceptionally well in a system of low offense phage. Now, when there are many prey around that happen to be low vulnerability, but because there are very few phage, then there can be a benefit for the high vulnerability types to invade. And as they do, that also comes with a rapid shift to high offense types, restoring then the virus population. Right? So we have a joint dynamics of population dynamics and evolutionary dynamics. And it's really driven by the concurrent change in genotype frequencies. Does this happen? Well, in work by Wei et al. Working with Bruce Levin, they had observed what they viewed as complex dynamics of Vibrio cholera and its phage, and cholera and phage have its own interesting story. What you can see here are dynamics that look, as I said, complicated, but we noticed something interesting here when we focused on a few sections, and I've highlighted them and raised them in the line width here so that you can see them. And I will then project these on the next slide into the phase plane. And what we found were there multiple examples of clockwise cycles. And there was actually further evidence that the system didn't just have a single host or virus, but in fact, they had found this T and B phage making turbid or big plaques and multiple kinds of resistant hosts. And what you can see here is that we have these clockwise-like dynamics where a system not only goes around the wrong orientation, but gets back nearly to where it started. Of course, one can raise a question, is this sufficient evidence for a clockwise cycle? And so what we did was in some sense take that time series and then create random time series that had the same point-to-point correlations, reconstruct synthetic time series, and ask how often would we see these kinds of short clockwise-like cycles, and then see if the fact that we found these should be a surprise. And the answer is yes, it was surprising despite the shortness of these cycles. The idealized clockwise cycle has a winding angle of 2 pi and goes back exactly where it starts. Here's the distribution of all these synthetic time series, what we observe in red. And just to point out that this is essentially as good as the lynx hair evidence as well, which is the canonical example for counterclockwise cycles or predator-prey dynamics. So we have as much evidence as we have essentially for these phage bacteria as we did for the lynx hair. Okay, so we have examples now of clockwise dynamics in this coevolutionary system. So just to sum up the second part, that more generally, whether we're talking about phage microbe dynamics or predator-prey dynamics with evolution in a general sense, Without evolution, we can only have these counterclockwise cycles in a qualitative sense. When either evolve but not both, we can have this, or we can have anti-phase cycles of the kind that you can see, or even these cryptic cycles where one is changing and the other is not. And when coevolution is included, then either of these two things can happen, but also it's possible to have clockwise cycles. Okay, so the take home here is simply that a rapid change in genotypes can impact ecology. Right? So when we think about virus microbe dynamics, we can't think as evolution is just turned off. And again, this is a natural consequence of going beyond Luria and Delbruck and asking what happened next, like Luria did in the 1940s, but not just on a plate that's static, but actually thinking of it as an intrinsic part of the dynamical system. But in this last part, in the last 15 minutes, I'm going to ask what other dynamics emerge in even more complex communities. And I should pause here again in case there are questions.
Yes, there are two questions. So Miguel, please mute yourself.
Hi, hello, Joshua. I have a question for the clockwise dynamics. Are we assuming in this system that the aggressiveness or the vulnerability have a fitness disadvantage or advantage beyond the viral microdynamics, or why else will the low aggressiveness genotype, for example, catch up again? Why
right, so we are assuming that there are trade-offs in traits. Okay. So I just said before, it's not inevitable. Just because you have coevolution doesn't mean you have to have clockwise cycles, right? There could be a replacement and we could just knock out one of the other kinds. Maybe the emergence of a doubly resistant bacteria, and even the fact that there's some trade-off in growth, it still knocks out the first kind. But there are particular conditions which we go into in this paper in which these cycles can generically be seen. But you're right that it involves trait differences, which I will elaborate on next.
Cool, thank you.
And there was another question by Ian.
Maybe we can, just because I've heard from Ion once and I appreciate that, but just to make sure that given there are hundreds of people here, maybe I'll just keep going to part 3, and Ion, you can send me or something in the chat just to make sure we hear from multiple folks. Is that okay, Jacopo?
Yes, okay for me.
So Ion, why don't you just send me put it in the chat and I'll answer afterward just to make sure that I finish up part 3. Sound good?
Sure.
Thank you so much. Very good. Okay, so let me go to part 3 and ask this last question, what is the relationship between infection networks and host viral dynamics in complex communities? As you can see, I've structured this talk focusing on single virus host dynamics, then 2 and 1, then 2 and 2, and this would be a very long talk, but I only have 10 or so minutes left. So we're going to try to make a leap of a kind, and this leap has been possible with really almost a decade of work by Cesar Flores, who began some of these projects, continued by Luis Jover, and continued even further by Ashley Coonan in the group now. And all these are physics students doing this kind of quantitative bioscience stuff, okay? And again, I'll go back to this notion that there are many viruses in these systems and pointing out that when you have this many viruses, they're gonna be quite diverse. We went back to some of these original data sets to really hone in on this question as part of a collaborative effort to analyze virus microdynamics in natural systems, finding that if we look at the number of prokaryotes, largely bacteria, and viruses per milliliter, you can see relationships. You may have heard this notion that there's 10 to 1 viruses per bacteria in natural systems. That's not necessarily the case, so that's a decent median. There's natural variability between 1 to 100 to 1. There's more of both in the surface than there are at depth. But the point I'm trying to say here is that there's a significant amount of variability, and there's also just a significant number of viruses. There tends to be many more viruses than there are bacteria in a typical ocean community, which means there's a lot of different types. And this has often been very hard to estimate because of the problem of rarity. So there's some early work, 15 years old now, which estimated the diversity in terms of species richness between 10,000 and 1 million viral genotypes. That's a lot. Also says that estimating is hard, and that estimating problem remains hard. There's something fundamentally hard about understanding the abundance of rare things because you don't see how many rare things there are because they're rare. So just a side note, but sufficient to say that these really are complex, abundant, and diverse communities. So how do we actually figure out who infects whom? We can't just keep going with these simple models. We actually have to look into natural systems. And so that's what we began to do to get a sense of what some of these relationships might look like and how that might explain coexistence. So what folks in the field had usually done is, like Lurie and Delbruck, collect bacteria and phage from the environment or from experiments or evolution experiments, and then see who infected whom. As you can see here, we have a plate of bacteria, and you can see as different kinds of bacteria exposed to different viruses, sometimes these viruses make these clear holes. These are plaques, which denote clearing. And then here they added the phage, but there was no clearing to note that this particular bacteria was resistant to this particular phage. People repeated this many times over, characterizing these as susceptible or resistant. And here you have one example of a paper in our digital version, just to point out that these are the same thing, where the blue background denotes the fact that the phage in the column can infect the host in the rows, and the white squares denote the fact that they can. When we looked at many such patterns across many different systems, we weren't sure what to expect. And if you look at this, you can't really see much of anything. And first we were disappointed. We realized, of course, there are many ways to display these particular results of phage bacteria infection experiments, because you have row and column orders, and this becomes a large, exponentially large number of combinations. So we used heuristics used to analyze network systems more generally to look for latent structure. And in fact, that's what we found. Examples in which it seemed like nestedness was quite typical. And what I mean by nested is that we have these, remember that viruses are in the columns and hosts in the rows. You can, let me see if I have an example. Yes, good. Here's the original data here, and here's the restructuring. This is exactly the same data. I just want to emphasize, same data. We've just shifted the rows and columns, revealing that this is in fact more of a nested structure, where we have these specialist viruses, which tend to infect a few hosts. It's not perfectly nested, but it tends to be so. And they infect the host that everyone else can infect. So the specialists seem to be infecting the easiest to infect of the hosts. And likewise, the generalists seem to infect the hardest hosts to infect, right? So the virus generalists are infecting both the easiest as well as the hardest. And you see that then the infection ranges are nested one within the other, and the same with the host. Okay? So even though this wasn't apparent in the original studies, it was clear that nestedness seemed to be quite typical, which raises questions. Okay? And the question it raises is, how do we have coexistence potentially between these specialists, which seem to infect the host that everyone else can infect, and the generalists, right? And likewise, why do we have hosts that seem to be infected by everyone hanging out with hosts that seem to be infected by almost none or very few? And just again to point out, this was unexpected. The nestedness in the original displays were quite low compared to the ones that we found with this revised sorting. And again, this means that we have these phage bacteria networks that are typically nested, and it's common in both ecology and evolutionary studies. So how can they coexist? So let me give a particular example here of one, why doesn't this most resistant host outcompete the rest? Right? It's only susceptible to one virus, but so is everyone else, and it's not susceptible to the others. And likewise, why isn't this most specialist virus outcompeted by the others? Same reasons. Only infect one thing, so can everyone else. What we've done is take these dynamical systems that I've already explained, but then using this letter I and J denote the fact that we have many types. So the hosts are competing, they're being infected and lysed by viruses, which are then releasing new virus particles back into the environment. And I'm only going to point out the fact that we have this matrix M, which we now are going to use something based on what the measurements imply, rather than early kill the winner models, which say there's one virus for every host, and clearly that could lead to coexistence. We're going to replace that with these nested models, raising the question of how do we have coexistence when we have overlapping niche or overlapping host ranges. And what we can see is that if we take a very simple community, when we have two viruses and bacteria together, in one case, only one coexists. You can see host one survives. Host one survives, and here we have virus 2 persisting and virus 1 going away. This other host may be at low density. And here we have both of them coexisting together, and they both have a nested network, but now the strains differ in their life history traits. Okay, so one case, one gets excluded, but in the other, all of them coexist. And they have the same structure, but it's the life history traits again that make the difference. If we solve for the steady states in the model, I'm just going to point out you see these kind of differences of traits, R2 minus R1, the differences in the infection efficiency. So it seems like these steady states depend on differences in terms of growth rates and differences in terms of viral life history traits. And the key points, without going into all the details, we've elaborated this for quite some time, is that if there is a growth rate that decreases with defense, so in other words, most vulnerable grows quickly, least vulnerable grows slowly, and likewise, that the efficiency of the specialist is high. In other words, it draws down hosts to low densities, whereas the efficiency of these generalists is not as high, right? It doesn't draw down the host to low densities. You can get arbitrary levels of coexistence. So viruses and hosts can coexist with arbitrary complexity. Now, this does raise the question, is there evidence for such trade-offs? And just to point out that typically when one looks for trade-offs, you see a tendency for there to be a growth rate resistance trade-off and a fitness and host range trade-off for viruses. But I'll also point out, here's strain and growth rate, all of these seem to be resistant to this particular virus, that there are examples in which there doesn't seem to be any cost. And likewise here, fitness on original host, no cost, even though now it has this niche expansion. There are other interesting stories here about contextual benefits of fitness, able to infect some but not other hosts, but again points out that these relationships are statistical in nature, just like those of the nestedness in these communities. And so in a separate work, we looked at the relationship between biodiversity, in other words, richness of this community as a function of nestedness, and only to find that nestedness does seem to promote diversity in the system, even if the nestedness is imperfect. And this depends on the life history traits. And we've done this for various kinds of life history trait assumptions and trade-offs, but again, the tendency remains. So just to finish up here, I'll just make one last thought and then I'll conclude, which is I've made a point here from single to multiple to these complex communities, showing that there is mechanisms of coexistence, whether through evolutionary dynamics or through trade-offs, but is nestedness the only feature? And I don't have time to fully elaborate, but I'll just give you a caution that most of the studies looking at host range and infection dynamics focus narrowly on a particular phage and bacteria within a species or genera. But clearly, if I have a phage of E. coli, it's unlikely to also able to infect Prochlorococcus and Synococcus. I can guarantee you it won't happen, right? So we clearly have differences at other scales. And just to point out that a long time ago, and we continue to work on related problems, we found that in these large scale studies of ocean systems, here was the original data, which we then restructured and identified modularity and found large scale systems did have modularity where the bulk of interactions happen within these modules. And so this just again suggests that it's not only nestedness, that there is separation. Some phage are infecting some types. What we found is these modules were correlated with geographic diversity. This is from an open ocean Atlantic sampling system. And even within modules, there tended to be nestedness. So in reality, what we expect is that true network structure is multi-scale, and that remains a challenge for the field as a whole. Okay, so I think I'm just on time and wrapping up, just to point out that trade-offs facilitate coexistence in this last part, that the abundance depends not just on who they can infect, but on life history traits, that these trade-offs need not be perfect for coexistence. Obviously, we saw that in terms of the nestedness. It was not perfect nestedness, nor was the trade-off necessarily perfect. But just as a caution, large-scale networks may have different structures, and I anticipate I'd run out of time, but we continue to work on actually the joint analysis of genotypes and phenotypes. And if you want to see some of that work, this is with Justin Meyer. It just came out on bioRxiv, going beyond just these phenotype assays and linking them to genotypes as well. And with that, I want to thank you for your time. I went over a lot of material, but my hope is that for many of you who are new to this area, this gives you a broad overview of some of the challenges as we move from microscopic dynamics to build population models, evolutionary models, and begin in the direction of trying to understand virus microdynamics and ecosystems. Thank you, and I think it's probably time nearly for a break.
Yes, so thanks a lot, Joshua. That was a fantastic broad introduction. So there are actually two questions. So if we can, think we can take 5 minutes for question. Okay, so there is one question from Leonardo.
Yes, thank you for the lecture, Professor. I wanted to ask, and I'm sorry if I'm asking something trivial, but I wanted to ask if there are explanations or intuitions as to why the relationship between phages and hosts is nested.
Right, so that's a terrific question, and one that has bugged me for quite a long time, because it seems to imply a kind of arms race dynamic. Is it a question of evolutionary constraint, or is it something about the ecology? And I won't open up my slide deck to be tempted to kind of give you yet another lecture on the questions, but if you look in our paper by Gupta et al., we begin to ask this, finding that in some cases it seems like it's really the ecology that's driving it, not necessarily a fundamental constraint from the evolution, from the, let's say, the biophysical side. It implies that there's an ability for a phage to then have this host range mutant without necessarily this earlier cost, right? And likewise, for there to be the possibility of becoming resistant to prior phage and yet still then being infected by a new phage type. So in a coevolutionary sense, it implies an arms race like dynamics, which would give rise to nestedness. But yet in this paper, Gupta et al., we show that even though that's what the phenotype looks like, the genotype implies that something else might have happened, but there was some trade-off or constraint ecologically that didn't permit a fluctuating dynamic, in which case you might expect modularity rather than nestedness. It's an open question, a terrific question. So I'll just leave it there, that it's one that we continue to try to explore. It really gets to the heart of what we're trying to figure out.
Okay, thank you very much.
Great. There is another question from Martina Dalbello.
Yeah, thanks, Joshua. It was really interesting. And my question is more a curiosity, I would say, because from what you told us, it seems that if there are very few generalist viruses and a lot of specialist viruses, and I see a sort of parallelism with the distribution of generalist and specialist in bacteria, because again, in natural systems, there are very few generalist bacteria and a lot of specialist bacteria. And I want to know if you have a comment on that, or you can, yeah, if you can comment.
Yes, so I guess I'll comment from the theoretical side that I didn't explain necessarily the relationship between the host range and the abundance, but you can actually go do that. And it turns out the model is flexible. So I know that may be unsatisfying, but it could be in the model predictions that the generalists are more abundant or even less abundant than the specialists. And it depends in some sense on their difference with respect to the most similar host or virus. I'd also caution that the generalism here is still narrow from the virus side, because we're talking about generalism within the context of probably a species or perhaps genera, not somehow beyond that. So just to caution, but you're right that it really depends on the life history traits and the trade-offs, but at least in the model, it doesn't say that absolutely one or the other will be the more abundant kind. But again, the cautionary, you're probably thinking about metabolic generalism and so on. And here it's just still narrow. So we don't yet have a sense, I don't think, enough quantitative data to give a definitive answer on the virus side. It's something we're still working on.
Great, thanks a lot. There is one last question by Miles, and then we'll take a break.
Yes, hi Joshua, thank you for the talk. I was hoping if I could get your opinion on particularly this connection between virus host dynamics and scaling up to ecosystem level consequences. The example that I had in mind was the unfortunate fact that we are currently destroying biodiversity at unparalleled rates. And how might the virome respond to this. Obviously, coronavirus is one example of this, but I just wanted to hear kind of your professional opinion on this, how we could understand ecoevolutionary consequences of this.
Yeah, so that is probably not a question I can answer even in 1 minute. To the extent to which we're thinking about that question, just because it's such an important, broad question, we have begun work, which I'd hoped it would almost be ready at this point, but it's still maybe a few weeks away, but hopefully it will be out soon on the bioRxiv, to embed these virus microdynamics in the context of ecosystem models, in which viruses are not the only agent of mortality, but that also includes flagellates and other protists that might be grazing upon target hosts. And so we really need to think about viruses as part of these complex communities. And once we start changing things, and particularly one of the things we could change are things like salinity, right? As well as CO2 levels or even temperature, that's going to change virus microdynamics in ways that frankly concerns me, but I don't know the extent to which that will start to impact long-term, let's call them microbial loop mediated processes. But I think we should be concerned that in addition to tampering or somehow upsetting biodiversity, we're also messing with ecosystem function. I'll point out that we do have one little speculative paper on micromonas viruses and hosts and effects putatively of temperature in long-term scenarios, where it implies that at least current viruses may have a hard time keeping up or infecting with certain bacteria, and to the extent to which they play a role in shifting the fate of dissolved organic material, that may also mean that it's really beginning to transform and change carbon and nutrient cycles at global scales. But at this point, that's all I can say, that we're at the beginning of that process, but that's one of the reasons we're focusing so much on these ocean systems, because of that shared concern.
Thank you.
Great. Thanks a lot, Joshua. So Joshua will give a lecture again tomorrow. And what we're going to do now is to take a 7 minutes break. So we are going to be again randomly assigned to breaking rooms. So if you want to stretch your legs, get a cup of coffee, I mean, please get away for a few minutes from the screen. But also if you want to take the opportunity to chat and discuss informally with other participants, please take this occasion as an opportunity to do that. So yes, so we'll be randomly assigned to breaking rooms in a few seconds.